Hello and welcome to Lab 3, Part B, Isostatic Equilibrium. In this lab section, we'll begin by asking the question, why is oceanic crust below the ocean? Recall our simple boat and seawater example of isostatic equilibrium. This example looked at how boat plus seawater and seawater columns exerted the same hydrostatic pressure on the underlying seafloor. Regardless of the weight of the boat, a constant hydrostatic pressure, or isostatic equilibrium, was maintained across the seafloor. This same principle applies to lithospheric columns of differing crustal thicknesses and densities that float on underlying plastic asthenosphere. Under all the columns, the hydrostatic pressure exerted by the material should be equal at some common depth. This common depth is called the compensation depth. In this part of your lab assignment, we will use a simplified cross-section of the continental margin to test whether equal hydrostatic pressure occurs at a common depth. In this cross-section, there are four columns: the mountain range, the average continental crust, coastal plain, and the average oceanic crust. Each column may be thought of as a columnar extension of Archimedes' principle, and each column extends down to a common compensation depth of approximately 150 kilometers within the asthenosphere. Also, each column is comprised of a typical thickness and density for seawater, oceanic crust, continental crust, and the mantle. Thus, given the density and volume or thickness of the columns, we can calculate the mass of each column to test whether hydrostatic pressures at the bottom of each column are approximately equal. For example, let's calculate the total mass for the average oceanic crust column as it's divided into three sections. To begin, recall that density is the mass per unit volume. Thus, we can rearrange the formula for mass so that the mass for the column equals density times volume, again, where the volume is the height of the column in meters, and it's a square column because we're assuming a three-dimensional column of 1 by 1 meters. Additionally, notice that our units of density are kilograms per cubic meter because our units are provided in this figure. Also, notice that the thickness of each layer in the figure is provided in kilometers. Thus, we will need to convert kilometers using the 1 kilometer to 1,000 meter conversion in our calculations. Thus, if we start with the top section of the average oceanic crust column, then we see that the mass of the seawater is the product of approximately 1,025 kilograms per cubic meter times 3,800 meters times 1 meter squared. When we cross-cancel units, we end up with the seawater mass of 3,895,000 kilograms. We then calculate the mass of the oceanic crust using the same formula. And finally, we calculate the mass of the mantle section, again using the same formula. When we add together the mass of each section of the column, we determine that the total mass of the column equals 490,685,000 kilograms. In your lab assignment, you'll repeat these steps and calculate the total mass for the mountain range, average continental crust, and the coastal plain columns. Before you work on your lab assignment, let's review some important assumptions. For volume, we are assuming that the column is measured 1 meter squared. In our conversion from pascals of hydrostatic pressure of kilograms per meter per times second squared, we will simply report density in kilograms per cubic meters to minimize unit conversions. And thickness must be converted from kilometers to meters using the 1 kilometer to 1,000 meters ratio. It's now time for you to complete your lab assignment. Complete lab assignment Part B, isostatic equilibrium. Once complete, watch video 4, Part C of isostatic adjustment. Please address your questions to your lab TA.